Okay, we are going to look at deciding on an extended free body diagram for this scenario with a painter painting a wall. So it says a house painter stands 3 meters above the ground on a 5-foot long uniformly distributed ladder that leans against the wall at a point 4.7 meters above the ground. The painter weighs 680 newtons, so we know the weight of the painter is 680 newtons. And the ladder has a mass of the ladder is equal to 12.2 kilograms. We're going to assume there is no friction between the house and the ladder. So this is a frictionless surface, but the ground and the ladder, thankfully, is not a frictionless surface, or that poor painter would be in a little bit of trouble. All right, so what we're going to do in this scenario is just look and analyze the extended free body diagram. So practicing extended free body diagram work. And we want to do that of the painter. So remember, with an extended free body diagram, we take the object of interest in this, not of the painter. Where's my eraser? Of the ladder. We take the object of interest and we draw it as a single object. Well, with the ladder, it looks about the same in the orientation. At least that's how I like to do it, in the orientation of its form. So here is our ladder. Then we're going to draw all the forces that are acting on the ladder where they are acting. And then we will look at both the radii, selecting a pivot point, the radii, and the angles. All right, so what forces do we have acting on the ladder? What's interacting with the ladder? And for the purposes of practice, we're going to do those force trees, those interactions. So we know we have the force of gravity. That is between the ladder and the earth. And remember, the force of gravity acts at the center of gravity, or the center of mass in our case. And so the center of a uniformly distributed object is the geometric center. So the force of gravity on the ladder is going to act directly at the geometric center of the ladder. So there's the force of gravity. Remember, that's mg. So we know that that mass of the ladder is 12.2, but to get the force of gravity of the ladder, we have to, of course, multiply that by 9.8. All right, that's one interaction. There's also an interaction between the painter and the ladder. So that's between the ladder and the painter. Remember, in our force trees, we put the ladder, the object we're interested, on top. The painter is standing a little bit past the center of gravity. And so we're just going to draw that painter here. And we have the force of the painter. And we'll say that's 680 newtons. We're given the weight of that painter, so we'll draw the force of that painter. All right, the ladder is also interacting with the ground. Now, so we do have the force of the ground on the ladder, but we can break the force of the ground up into its two pieces. One is the ground has a frictional force associated with it, and that's a static friction. The ladder is not moving or changing its motion, so that's between the ladder and the ground. And the other piece that the ground is exerting is that normal force, upwards, holding that ladder up. So that's between the ladder and the ground. So we know that the normal force is, of course, going to be in the upward direction. So we're going to put the force of the ground here that's equal to the normal force. And that little g means ground, not gravity. And if there was friction, if there was no friction, the ladder would move that direction. It would slide down and out. So friction must be opposing that motion. We can say that the force of friction of the ground is acting in that direction. All right, and then the last force that we can examine is the force, I did that in pink, well, that's okay, the force by the wall, and that is a normal force between the ladder and the wall. So the wall is leaning against the ladder. We have the force of the wall here, which we're going to call that normal force. And since there's no friction on the wall, That's the only force that the wall exerts. All right. So these are all of the interactions that are happening with the ladder. We have the earth, that's gravity, the painters on it. The ladder's interacting with the ground in two ways, the normal force and the force of friction, and then the force of the wall. Now, to determine the radii and the angles, another good important point on a extended free body diagram, we need to select a pivot point. And so let's select the pivot point of the ground. Now, if we select the pivot point of the ground, the radius of the normal force and the radius of the force of friction of the ground, in this case, are both 0. All right, so we're going to ignore those because the radii are both 0, and therefore they're not exerting a torque if our pivot point is selected there. And we're going to look at the radii of the 3 other forces with respect to that pivot point. So here is the radii with the force of gravity, and we're told that it's a 5-meter long ladder, and gravity acts at the geometric center, so the radius is 2.5 meters. The radius of, so this is the radius of G. We then have the radius of the painter. All right, so in order to determine the radius of the painter, we have to sort of look at our scenario in terms of the geometry. Okay, so what do we have here? We want to know this angle. If I knew this angle theta, and I know this height, 3 meters, I could get the radius along that hypotenuse. So how can I get this angle theta? Well, the full length from the ground to the wall is 5 meters. So I'm going to redraw my triangle. This is 5 meters. And we know that the ground stands 4.7 meters in that direction, up. So this angle theta, the opposite, 4.7, the sine of theta, sine is the opposite over the hypotenuse. The opposite, so the sine of theta is going to equal the opposite, 4.7, over the hypotenuse of 5.0. So theta is the inverse sine of a 4.7 over 5.0, which equals 4.7 divided by 5.0 is 0.94, and the inverse sine of that is 70 degrees. So this angle here is 70 degrees. All right, so if I know that angle is 70 degrees, I can draw another triangle, because again, I'm trying to get the radius from the pivot point to the painter, wherein this is still 70, and this now is 3 meters high. And we want to know what that side is. And again, the sine of our angle is the opposite over the hypotenuse. So the hypotenuse is the opposite over the sine of our angle. So we have 3.0 over the sine of 70. So 3.0 divided by the sine of 70 equals 3.19. All right, so our radius for the painter, let's use the same color, is 3.19 meters. So that length. Okay, and then the last radius we're interested in is the one of the normal force by the wall. This is the normal force of the wall, not to be confused by the normal force of the floor. And that's the full length of the ladder. So here are our radii, and the other thing we want to think about are our angles. So we need the angle of the force of gravity, the angle of the painter, and the angle of the normal force of the wall. So how do we find those angles? And again, in the learning class, my right hand is your left hand, so you'll have to just sort of mentally make that change as you look at the right hand rule. So we point our fingers in the direction of the radius. So for the force of gravity, We're going from the pivot point to the force, and then we curl our fingers in the direction of the force. So this is the angle we're interested in. We know that this part here is 70 because this part here is 70. So 70 plus 90, we have an angle of negative 160 degrees. And why is it negative? Because I'm going in the clockwise direction. The force of the painter is going to be the same as gravity. They're pointing in the same direction, so their angles are going to be the same. We put our fingers in the direction of the radii, extend that radius, and then curl to the force. And again, we get negative 160 degrees. All right, and then our last angle that we're interested in is the angle of the normal force. So again, we point our fingers in the direction of that radius. Oh, I didn't draw that on there. There's the radius of the normal force of the wall. We extend that radius and curl in the direction of the angle. And this gives us that angle there. We know if this is 70, this is 70. And this hole is 180. So our normal force of the wall is 110 degrees. All right, so again, just looking at those angles, we're interested in extending that radius and curling to the force. This is 70, this is 70, so 70 plus 90 is 160. It's in the negative direction because it is a clockwise angle. Similar for the painter. And then for that normal force, we extend that radius and curl to the force. Okay, so our extended free body diagram looks like this. And then we have to identify, of course, all the radii and the angles. All right, we're going to use this process to analyze statics and net torques on an object to get those rotations. Good job.